Hello and welcome to part one of the Introduction to Image Velocimetry. These workshops have been designed for students primarily who want to look at using image velocimetry to capture and process some surface velocity data towards their own research. Part one has been designed to explain what the image velocimetry is and why it can be so useful to us. So the overall aim of this presentation is to introduce the absolute basics of image velocimetry and why we tend to use it over other techniques. And we can hopefully begin to use this information in our own analysis of videos. But by the end of the presentation, hopefully you're going to understand what data is needed for the processing and what outputs we can get from that. Of this short presentation, I just want to cover two main areas, and that's the fundamentals of image velocimetry and a couple of examples of it being used. Crack on with looking at the fundamentals of image velocimetry. So to look at the fundamentals, we're going to look at what actually is image velocimetry, and then we're going to look at what its origins are, how does it actually work, and then why do we actually need it in modern river settings. So what is image velocimetry and why is it so important that I'm talking to you about it today? Image velocimetry is a technique that can automatically detect and track points on a river surface to find their displacements over a known period of time. So at its absolute basics, it's basic maths and physics of distance over time to find a velocity. To do this, it uses everyday cameras that can be situated either at a fixed point, like a CCTV camera, or it can be more mobile, like using handheld cameras, mobile phones, or even drones. These videos are then put into a software that uses algorithms coded to automatically detect the movement of tracers within your region of interest. Now, these methods aren't new by any stretch of the imagination. They've been noted to be as early as Leonardo da Vinci, who would artificially seed river surfaces and then just draw their interactions with the river surface. Then, if you fast forward a few hundred years, you've got Ludwig, who would use cameras to capture aerodynamics around objects and their fluid boundary layers, used mostly in aeronautical engineering. It goes all the way forward to what we see today with modern methods used in large-scale settings such as rivers and streams. So why is this method so important? Typically, when we want to monitor things such as rivers and discharge rates, we would have to implement something like a pressure gauge or something that sits in the water and measures it intrusively. That can cause problems long term with high flows causing damage or debris and weeds interfering with the apparatus, etc. But other methods such as ADCPs, they also rely on the touching of the water, and that can cause a real risk to both the equipment and the operator, especially in high flows. The beauty of IV is that all of the need for intrusive measurement is taken away. Cameras can be situated far, far away from the rivers, increasing both the operator safety and making data capture a lot more simple. Another thing to consider is the remote sensing aspect that can be made. So fixed stations can actually be set up in a way that automatically captures and transmits the data over to us from mobile networks and through cloud storage. So several sites worth of data can be captured in the same day from a desk. We can also fly out drones to areas that aren't so safe to get to, down reaches that we'd typically not be able to sample. That saves us so much time and effort compared to the more traditional methods. So now that we've understood the basics of what image velocimetry is, let's have a look at a couple of examples of what we'd want to get from image velocimetry, some of the outputs that we'd typically see. So like I said, there's these more modern methods of image velocimetry. So what are those? These images show you the two types of image velocimetry that are available to us. The left-hand side splits the image into grids, and each grid is associated by a velocity vector given the particles that pass through it over time. And we call this method PIV, or particle image velocimetry. The images on the right-hand side have a slightly different approach. These methods detect a tracer and follow its path between frames until it's lost. This pathway is then drawn onto the surface and associated with a velocity. We call this method PTB, or particle tracking velocimetry. Both of these methods have been shown to be reliable at recreating surface velocities, but there are some fundamental differences in each, which makes one advantageous over the other. I'm not going to go into more depth on this now, because I go over this a lot more in depth in part 2 of the introduction to image velocimetry. The examples I showed you on the previous slide are examples of fixed cameras. This is an example of a drone flying over a reach and capturing artificially placed traces. It's a very slow moving river, so it can be quite tough to see the traces, but with the video being grayscaled and the background removed, it actually helps the algorithm track the white traces that are seen floating in the image. The two arrows that are on the edge of the river are highlighting some GCPs, or ground control points, that were placed to help stabilize the image. The two arrows that are placed in the stream show where the traces are floating if you're struggling to see them. The results we get from this video are shown in the bottom right. And you can clearly see the change in velocity from the edge of the bank, but also how there's a lack of traces in some sections of the video. For good, reliable data, we would hope to see results as uniform across the river as possible. So it's safe to say for this video, either more video was needed so that the traces had time to flow all the way to the top of the image, or more traces were needed and dispersed more evenly. If that still didn't work, then you would have to look at other considerations as to why it's not working in that area. Sometimes we see issues with lighting causing the algorithm to lose traces and fail their displacements. And these are all things that you have to consider when you're starting to capture data for the first time. So that's the end of part 1. It's a very short presentation on just what image velocimetry actually is and some of the outputs that we can expect to see from it. Next up is part 2, and I'm going to start looking at more detail on some of the things that you need to think about if you're going to start capturing this data for yourself and then processing it, and more examples of some of the discharge readings we can get from it.